In this video, we are going to take a look at something very closely related to the equilibrium constant, and that is the reaction quotient. Now, the equilibrium constant is a measurement that is taken at equilibrium, or when a chemical reaction reaches equilibrium. The reaction quotient is something that can be measured at any point during a chemical reaction. Let's go back to our swimming pool analogy where we had sunbathers and swimmers. And these sunbathers and swimmers at 75 degrees Fahrenheit on this cloudy-ish day have now reached equilibrium. So the point where we have 9 sunbathers and 3 swimmers is our equilibrium at this temperature. So the K is equal to the products, or 3 swimmers, divided by the reactants, which is 9 sunbathers. And if I calculate this out and put it into decimal form, we get 0.33. So that is our equilibrium constant for this reaction of swimmers and sunbathers. But let's just say we have a mixture of sunbathers and swimmers at some point in our reaction. It could be maybe an initial starting point of a reaction, and we have a total of only 2 sunbathers and 10 swimmers. Let's write this reaction out. So sunbathers are in equilibrium with swimmers. And the sunbathers are just hanging out on the side of the pool, and the swimmers are in the pool at this temperature. Now remember, the K for this reaction is equal to 0.33. That is the equilibrium constant, or the comparison of products to reactants at 75 degrees Fahrenheit. So the current situation, what we're dealing with right now, is we have 2 sunbathers and 10 swimmers. Now the reaction quotient, this is something that we can measure at any point in a chemical reaction. It could be initially, or a few seconds after the reaction has started, or a couple hours after the reaction has started, at any point in the reaction. So we're going to say at this point we have 10 swimmers and 2 sunbathers. So the ratio of swimmers to sunbathers is 10 to 2, or 5. Now we can see that this is significantly greater than 0.33. So we have 5 is greater than 0.33. And what that tells us is that the swimmers are probably going to get out of the pool to reach equilibrium. That 5, by the way, we're going to call that Q. That is the reaction quotient. So just like K, however, it can take place at any point in the chemical reaction, and it's calculated exactly the same way as K. Whereas K is calculated only at equilibrium. So the fact that Q is much larger than K tells me that swimmers are going to get out of the pool because equilibrium wants to be reached. And in order to reach equilibrium, swimmers are going to need to turn into sunbathers, or products are going to need to turn into reactants. So let's set up how we would calculate the reaction quotient. This probably looks very familiar to you because this is exactly how we calculated the equilibrium constant. If we have a reaction of A plus B equals or creates C plus D, then we write our products raised to the power of their coefficients over the reactants raised to the power of their coefficients. So let's take a look at what this means. The reaction quotient is useful because we can compare it to K. So we will be comparing Q to K. It's not useful by itself. It's only really useful in comparison to K. And if Q is less than K, then the reaction will progress toward the product side, or more reactants will turn into products. If Q is equal to K, then we know our reaction is at equilibrium. If Q is greater than K, as it was in the swimmers to sunbathers example, the reaction will progress towards the reactants. Let's take a look at some practice problems. So if we have the reaction of 2 sulfur dioxide molecules reacting with an oxygen to create 2 sulfur trioxide molecules, the K at this temperature for this reaction is 3,900. So the K is equal to 3,900, and it asks us to write the equilibrium constant expression for this reaction. So we're going to take the products raised to the power of their coefficient, so raised to 2, the second power, over the reactants SO2 raised to the power of its coefficient multiplied by the other reactant, and the coefficient there is 1, so we don't have to really raise it to any power. Now we're going to write the reaction quotient expression for this reaction. Guess what? It looks exactly the same. We calculate these two numbers out exactly the same way. The equilibrium constant expression is measured at equilibrium. The equilibrium quotient is measured at any point in a chemical reaction. So let's say a reaction vessel contains 0.150 molar sulfur dioxide, 0.150 molar oxygen, and 2 molar sulfur trioxide. Predict the direction the reaction is going to shift in order to reach equilibrium. So we're going to calculate the Q for this. We're going to substitute our numbers in place of the, in those placeholders where we put just the concentrations. So we have 2, or the concentration of the sulfur trioxide raised to the second power over 0.150 raised to the second power multiplied by 0.150 raised to the first power. Those are my concentrations of the reactants. Multiply this all out, put it into a calculator, make sure you're using parentheses around the denominators multiplied together, and we get 1,185. Now, what we're going to do with this Q is we are going to compare the Q with the K. So the K is 3,900, the Q is 1,185, so the Q is less than the K. Now, because we're comparing these, and we can only really just compare, because we're comparing these and the Q is less than the K, the reaction will shift in a certain direction. We don't have an equilibrium. So which direction will the reaction shift towards? Well, in this situation, the Q is less than the K, so the reaction will shift toward the products. If the Q was greater than K, the reaction would shift toward the reactants, or shift to the left. Let's take a look at this example. If we have 2 molecules or 2 moles of hydrogen iodide breaking down into hydrogen and iodine, the reaction constant, or the equilibrium constant for this reaction at 25 degrees Celsius is 0.25. If a reaction vessel contains 0.500 molar hydrogen, 0.500 molar iodine vapor, and 0.750 molar hydrogen iodide, which direction will this reaction shift to reach equilibrium? Well, I substitute my numbers in place for the values, 0.500 times 0.500 over 0.750 squared. Remember that hydrogen iodide has a coefficient of 2, so we have to square it in our quotient expression or our equilibrium constant expression. Multiply all of this out, and I get 0.444. Now, my equilibrium constant was 0.25. My equilibrium quotient, or my quotient for this reaction, is 0.444. So the quotient, the reaction quotient, is greater than the equilibrium constant. What this tells me is the reaction will shift toward the reactants. And there are too many products for this reaction, and the products will then go backwards and turn into reactants.